Thank you, Graham, and good morning, ladies and gentlemen. The title of my speech is Silicon Photonics, Bigger is Better. So Graham very kindly introduced my background, and I'd like to put this talk into context in terms of that background. So the idea of silicon photonics was proposed in 1986 by Richard Soref. And one of the main issues that he saw in the field of silicon photonics, in the idea of silicon photonics, was the ability to produce a single-mode waveguide in silicon in a practical way. And up until that point, there had been no success in this area. His thoughts around this approach were to create a waveguide structure which was similar in terms of dimension to the photonics devices that already existed in material systems like lithium niobate and 3,5s, and in silica and compatible with silicon optical fiber. So these were waveguide structures of a few microns in dimension. I founded Bookham in 1988, and then soon after started working with Graham at the University of Surrey, where Graham was based. And we also worked with Richard Soref and others on pioneering the basic structure that would enable silicon photonics to evolve and allow us to leverage the trillions of dollars investment in the silicon microelectronics industry to make silicon photonic circuits. So the company grew steadily through the 90s and was invested in by Intel and Cisco. We had two fabs manufacturing these chips, and we developed a highly automated back-end assembly line. The company did a very successful IPO in 2000, and as Graham mentioned, the company is called Aclaro today. On this slide, we list the three main product lines that were produced. These were Telcordia-qualified products that were produced in volume. And the highest volume was a bidirectional optical transceiver. And as you can see here in the diagram, it consisted of silicon waveguides, the attachment of lasers and photodetectors, and the integration of an optical connector and facet for the optical fiber. What I'm holding in this photograph is that product, and there's a version of it down in the right-hand corner of the slide. We also produced array waveguide gratings and high-speed variable optical attenuators, which were based on a silicon diode. So Bookham pioneered the multi-micron wave platform optimized for photonics. And then subsequent to Bookham, I went on to chair and be the main investor in Katura, where we continued the development but focused on introducing some of the active devices as monolithic devices into the silicon. And we sold Katura to Menelux in 2013. And after that, it was a clean sheet of paper, and we started all over again with all of that experience with Rockley Photonics. So what are we looking for out of silicon photonics? We are looking at a planar process, a planar structure which integrates optical functions, allowing a single chip to integrate waveguides, all sorts of modulators, detectors, multiplexers, demultiplexers. We need to have light sources integrated, and 3,5 materials deliver those best light sources, so we need to find ways to integrate that. And we need to come up with a solution which ultimately has many fewer components, is much smaller, lower power, and no reduction in terms of performance. We must maintain performance. And the overall goal with maintaining performance is to reduce manufacturing complexity and cost. So delivering reduced cost requires a photonic platform enabling low-cost automated manufacture. So a little bit more of the up-to-date history of silicon photonics and the commercialization of silicon photonics. So the history of Bookham and the extensive nature of what we developed in the product range was somewhat lost in history by the dot-com crash. So for many people, the history of silicon photonics starts around about 2000 with the beginning of publication of work from Intel and other groups in this area. And this sort of era of silicon photonics has been based upon the idea of adapting a CMOS process to make optical circuits, with the idea that this could be very cost-effective, and also the exciting prospect that everything could be integrated, photonics and microelectronics. So what's happened since that dream was first introduced? So there are over 10 separate photonics companies, each in their own way, with their each unique approach here. But the vast majority of the work leverages sub-micron CMOS process technology used today to make large ASICs. Products have come to market from, so far, a relatively small number of vendors and have, as yet, not fully displaced alternative solutions. So in the past 15 years or more, silicon photonics has not yet achieved its full volume potential. So with silicon photonics, we aspire to something like Moore's law, to achieve silicon scale. For the microelectronics industry, small process geometries have enabled exponential advances in performance, integration, and cost. So just continuing to make everything smaller and smaller over time has served us extremely well. Moore's law, up until now anyway, has never let us down, and we continue to rely on it for data processing, communications, and fast electrical I/O. However, a question arises: why hasn't silicon photonics followed the same path of exponential growth? If we look at the 30 years since the beginning of silicon photonics, the progress from a commercial perspective and impact on our life has been a great deal slower than it has for the mainstream microelectronics industry. So we can benefit from revisiting some of the foundational assumptions back in the late 1980s. Photons behave differently to electrons. After 30 years, photonic-based products design is still dominated by considerations of material integration, light coupling, manufacturability, yield, and assembly. And it's worth noting that we really need quite a wide range of materials and material systems to achieve all of the photonic functionality that we want. And when we compare a transistor today used in a CMOS process, even though it's extremely small and very clever, that its performance characteristics are actually relatively poor compared with the functionality that we're trying to create in semiconductor optoelectronic structures. So we have a very demanding problem on our hands. Many of the challenges in contemporary photonics can be attributed to the physics of deep submicron silicon processes. As I mentioned earlier, up until the advent of this idea, and for that matter, all other commercial photonic devices use waveguides of a number of microns in dimension, or the mode size is a number of microns. Yet submicron CMOS-orientated silicon photonics is an order of magnitude smaller. So solutions are revealed by increasing the dimension in the process. Every photonic platform brings different engineering challenges, but it's really, really important, and it really matters where you start on that journey to solve the problems of a full and complete integrated photonic process. So here's a wish list of what we want, a vision of silicon photonics to enable volume scale. We need high-yield wafer processing with good process control. So that's not just being able to demonstrate that you can make something, but the process can control the parametric yield and deliver you the performance. We need a high-throughput fiber assembly process. We need low-loss optical waveguides, and we need low loss throughout the entire system to avoid the laser power becoming a dominant part of the power consumption of the system. We need high throughput integration of other material systems, including 3-5 materials, which of course are particularly good at creating lasers. And we need high channel density with small active structures to integrate with microelectronics. And we need the active structures, low power modulators, as an example, that can be driven by leading edge CMOS technology. And we need high throughput, high yield assembly sequences. How do we put these silicon photonic devices together? How do we integrate them with the rest of the system? How do we integrate them with microelectronics? And how do we control them in varied and different environments? And we need a process technology which can be as pervasive as microelectronics in order to get this silicon scale. So we can't just look at one application for the technology. We need to look at a vast array of applications which photonics can be applied to and ensure that our process technology is able to address these. So the right attributes will bring out the silicon scale potential of silicon photonics. So let's start with high-yield wafer processing with good process control. So process control is key to high yield. A volume process must demonstrate performance to spec across reasonable process variations. And here in this slide, I use the example of a wavelength division multiplexing device, a demultiplexing array waveguide grating. And when we look at making this structure in waveguides, in silicon waveguides of the order of 3 microns, then we can see across the semiconductor process control capability that the best that silicon processing can achieve in terms of line width and film thickness control and etch control, that we can easily meet today's requirements of wavelength registration and for those in the future, here in this example, to 0.1 nanometer registration. If we make the waveguide of the order of 10 times smaller, then that registration becomes very much more difficult. And with the very latest manufacturing technology, we are unable to meet anything that would be practical from a wavelength registration for any application. So in order to overcome this problem, we're going to have to add further functionality and control to our optical circuit to compensate for it, which will be power and cost and limit the applications. So large waveguides, typically above 1 micron, compared with sub-micron waveguides, can be of the order of 25 times more tolerant to process variation. High throughput fiber assembly is probably the single most important from a cost perspective of any photonic device. One can make beautiful photonic devices on a wafer scale, but if you cannot get efficient coupling to an optical fiber and do it in a high volume manufacturing way, then you haven't solved the fundamental cost problem. So mode expansion to large diameter fiber, core fibers, poses a challenge for small waveguides. A large waveguide is amenable to structures that are necessary to directly couple to optical fibers. So on the left-hand side of this diagram, you see the mode profiles for a 220 nanometer waveguide, typical of a CMOS-derived process. Highly polarization dependent. The mode overlaps heavily with the edges of the waveguide. And it's difficult to expand this mode efficiently to a larger mode size that would be compatible with an optical fiber. You can add additional material systems to address this, but they all add further loss in this process. To directly couple from these waveguides to an optical fiber needs grating couplers, which are difficult to produce with low loss. They're relatively large. They tend to be highly polarization dependent and can be wavelength dependent. So progress has been made in this area. Losses are coming down, but you're fighting against fundamental physics to achieve sub-1 dB losses. On the right-hand side, we see the mode size of a 3-micron waveguide, and it's not polarization dependent. The mode is pushed away from the edge of the waveguides, the regions in which you could experience scattering. And though it's possible to taper down this waveguide to smaller waveguides, it's very easy to adiabatically taper these waveguides up to a mode size that's necessary to match a single mode optical fiber. So passive efficient coupling to single mode optical fiber using an on-chip adiabatic taper. And that in itself facilitates the embedding a fiber-attached structure which you can use in passive alignment. And the structure is polarization independent and can be repeatably below 1 dB insertion loss. So the connection that you see here is like an optical fiber connector. It basically has the alignment properties of such a device, so it can be a passive alignment process. It's essentially building a connector with the same properties as a conventional optical fiber connector into the chip itself. So large waveguides are best suited for low loss, high throughput fiber attachment to the chip. Now let's look a little bit more at the physics of these larger waveguides. As I've mentioned, this type of waveguide can adiabatically taper up or down in terms of size. The business size of that waveguide, where you get the optimum characteristics, are typically, as I say, above 1 micron and between 1 to 3 microns. Multi-micron waveguides provide high confinement of light, intrinsically low propagation loss, low field overlap with sidewalls, low index sensitivity to sidewall variations. TE and TM modes have the same shape. It's polarization independent performance. Spatial intensity is low, low non-linearity, high power handling, which is incredibly important for actually the vast majority of applications for silicon photonics, and single mode. And quite remarkably, single mode over a very broad wavelength range. So one structure can be single mode over microns of wavelength. So waveguides can be designed to operate in this single mode regime. And what happens is the higher order modes in the correct design radiate into the slab. And as you can see on the mode propagation images on the right-hand side of the picture here, that if you launch into one of these waveguides that's designed to operate as single mode offset, you will excite higher order modes, but these dissipate and radiate into the slab over a relatively short distance. This diagram brings together some of the points that I've discussed in terms of the difference between waveguide sizes. So on the left, we see the smaller sub-micron waveguides, and on the right, we've taken 3 microns as a comparable point. And we can see the wavelength sensitivity significantly lower. We can see the power handling and therefore the number, for example, of wavelength channels that you can operate with being significantly higher. We can see the waveguide coupling to optical fibers being considerably lower, and the waveguide loss itself considerably lower. And when those optical circuits have that much lower loss, then you can build far larger and more complicated circuits within the same link budget. So micron plus waveguides have 10 times lower waveguide loss and accommodate 100 times optical power or number of channels. So how about the other material systems that you need with silicon? The idea of limiting yourself to silicon as the only material system to particularly build the active devices in silicon photonics is extraordinarily limiting. And so a platform needs to be able to accommodate many different material systems. And as there are further development in material systems in the future, one wants to be able to integrate those materials as well. So photonic circuits integrate multiple material systems. Large waveguides enable the easy alignment to high-performance existing 3-5 structures with low loss. And there is clear benefit in this regard in terms of using this capability to integrate lasers in particular. But it's not only limited to laser structures. Another way of looking at it is silicon photonics in our idealized platform, as we're talking about here, isn't silicon. Silicon is just part of it. Silicon is perhaps the workhorse, but upon that you need other material systems. You need, in the main, to integrate 3-5 materials with silicon. So enabling a broad product line is you require heterogeneous material or monolithic material integration with silicon. So what about density? And the title of this talk is Bigger is Better. So would not bigger waveguides mean larger optical circuits, which would mean less compact and less cost efficient? Well, no, that isn't the case. That in fact you can make very small optical circuits in large waveguides. You can make the light go around very tight bends. The example graph in the middle here shows 44 180-degree Julia bends with a loss measured less than 0.02 dB. It's really quite remarkable. So there is no limitation, there's no penalty that you're paying by using a large waveguide to produce compact optical circuits. And on the right-hand side, we see the necessity for compactness. We need structures that are small, that are going to integrate, for example, with the SerDes pitch in CMOS ASIC technology, and they're going to meet the pitch of optical fibers, all of which can be achieved. So let's look at the modulators. And I've taken 2 examples here. It's by no means all of the examples of modulator design. On one hand, I've looked at small waveguide, submicron, Mach-Zehnder modulators. And on the other side, I've looked at modulators that are based upon shifting the band edge of the material system, Franz-Keldysh effect. And these 2 principles are actually the principal approaches for producing modulation, high-speed modulation, in the growing data center market for single-mode optical fiber transceivers. So larger waveguide, what does it mean? It actually means smaller modulator. A submicron interferometer structure can occupy 50 times larger area than an EAM doing the same job. Now that's not to say that phase modulators and Mach-Zehnder structures are not important throughout many other applications in silicon photonics, and they can be produced in larger waveguides. But just in this example, larger waveguides means smaller modulators. Low power modulators and interface to electronics is incredibly important. Power is everything, density is everything, compatibility, as we push photonics closer and closer directly to integrate with high-performance CMOS technology. It's incredibly important that we have low-power interfaces to electronics and compatibility with leading-edge CMOS electronics. So this type of technology is high bandwidth, O-band modulators, and they can be implemented in these large waveguides with voltage requirements that are completely compatible with drives that can be produced in leading-edge CMOS technology, 28 nanometer, 16 nanometer, 7 nanometer. So the modulator influences the electrical interface circuit, which drives multiple considerations in assembly. So let's look further at the power consumption. Large waveguides, small modulators equals lower power. And one of the reasons for this is we need to make structures that are typically less than 100 microns in length in order to make them a lumped element that can be driven directly from leading-edge CMOS. Any larger than that requires a considerable level of increased complexity in the drivers. So submicron interferometric structures for the application I've mentioned require high electrical power to achieve modulation effect. Part of the issue here is also a material system problem, that the principle used in small waveguide phase modulators for this particular application is a reverse bias PN junction, and it's a relatively weak effect. Whereas the Franz-Keldysh effect, which is also requires a reverse bias PN junction, is a very powerful effect. Similarly, the material system that we're using to make these type of modulators is also applicable to very efficient phase modulation as well. So one can build very compact phase modulators and Mach-Zehnder structures, all meeting today and future bandwidth requirements of optical communications and other optical applications. So moving to the market considerations here, it's vital for silicon photonics, if it's going to be as pervasive as microelectronics, as silicon microelectronics, that your process technology is able to address the widest range of applications. And to date, there has been a principal focus in this area from a commercial perspective on communications, which may well turn out to be actually quite the smallest market. Still a very big market, but there are even bigger markets. So the use of the technology in robotics, spectroscopy, vision systems in the automotive industry, 3D imaging systems in consumer, advanced forms of computing, and more dense applications in chip-to-chip optics. All these markets add up to many, many tens of billions of dollars, and considerably larger than one single market listed here. So these have very profound impact on the development of the process technology, and ultimately its economy of scale. So, for example, one element that we looked at here was the power handling ability of your waveguide. And so the power handling capability for many of these applications exceeds what is capable of a waveguide of 220 nanometer dimension. So where do we go from here? Well, as I mentioned, a very important market is the cloud computing market. And cloud computing will enable further mega-scale volume in silicon photonics. We are heading towards the design-in and transition from 100G modulation to 400G modulation. Today, the world is ramping up with 100G modulators for data centers, 100G transceivers for data centers, and this market will continue to grow strongly in the coming years. But we're already at the point of architecting and designing in the next speed point, 400G. And as you get to these higher speeds, there is a transition in terms of where you want to place that photonic interface. And so there is now strong interest in what we call in-package optics, integrating that interface directly to the digital world. This requires photonics with extremely high performance, very low power consumption, direct compatibility with leading-edge CMOS technology, and a very high-yield assembly process. So a platform with high throughput, high yield assembly is the #1 consideration to achieve silicon scale. And one's got to do all of this without compromise to performance. The diagrams that we see here are illustrating the transition from discrete ASICs in an RU box and discrete optical transceivers, and integrating far more transceiver function than you would see on the front panel of the left-hand example, directly around leading-edge ASICs, which can be today of the order of over 12 terabits of capacity and will continue to grow. So just think of that in terms of how many 100G transceivers that represents. It's difficult to imagine integrating that much into a single package around an ASIC, but that's what is needed and that is what is possible. So the IC industry onwards to integrated optics, and the basic physical reason for this in the communications industry, in the computing industry, is as electrical SerDes get faster, then the distance over which they can, in practice, drive their signals gets shorter and shorter. And we're now at the point with this transition from 100G to 400G standards that we're not able to transmit economically electrical signals even within the rack of computers in a data center. So this is the primary shift to in-package optics. It's inevitable, it's predicted by the industry, and the solution is required now for deployment in a couple of years. As the reach of electrical links decrease, optical links must move right up to the ASIC. So hopefully I've got my message across of what was intended in the title. Bigger is better. Smaller is better in the microelectronics industry. That's Moore's law. It's served us well. But we must think, why has silicon photonics moved actually so slowly from a commercial point of view compared with the microelectronics industry over at least the last 20 or 30 years? And this does suggest a reconsideration of what are the parameters that are important, and understanding that those parameters, in order to create silicon scale, are actually not the same as the microelectronics industry. We can benefit from everything within the microelectronics industry, the precision at which we can make things, the wafer scale, all of the process technology is of value. But how you bolt that process technology together, how you integrate it with other material systems, is the way to create the optimized process which will meet and fulfill the requirements of a pervasive silicon photonics process. So as we make this comparison between big and small, we find that bigger means 25 times better manufacturing tolerances, 10 times less waveguide propagation loss, allowing us to build bigger circuits within the same optical link budget, higher yields, higher throughput, lower fiber coupling loss, facilitating low-cost, high-volume assembly, polarization independence, high yield, high throughput integration of 3-5 materials, heterogeneous or monolithic, compact circuits produced with tight bend radius circuits, waveguides, the amenability of compact modulators enabling low-power single-stage CMOS drive circuits, allowing you to drive directly out of the digital CMOS world into the photonics world, and the capability of supporting optical modulators across the full range of wavelengths. And as I mentioned, this is, with large waveguides being single mode over a wide range, this is a platform technology which has microns of optical bandwidth. So driving silicon scale means focusing first on what's needed for high volume manufacture and ensuring that you deliver that with high performance as well. Thank you very much for listening to me. We have 5 minutes left, so I can open the floor to questions. Thank you.